So as Paul said, my name's Alex. I'm a PhD student at SW. My whole focus is specifically on reinforcement learning. So I really like talking about this stuff. I'm glad some people came to listen. Just a bit of background so you know kind of... Louder? Just so you know kind of who I am. I did my undergrad in Brisbane at UQ, electrical engineering. I went to Germany and did a master's in electrical engineering there. And then while I was there, I kind of got exposure to some robotics stuff, and I got to see, I did a course in reinforcement learning. I got convinced it was like the most awesome thing ever, and I decided I wanted to do it for 4 years. And I came back to Australia and joined Alan's lab in SW. So I kind of want to begin with a bit of throat clearing about what I'm actually going to talk about here and what I'm not going to talk about, because I get really, really frustrated when I see other people do talks and they start a broad brush overview lecture with really detailed specific like things like maths and implementation details. So I'm going to really try and not do that, right? I'm going to try and give you guys a really broad feeling of how this kind of area works, how we can go from tabular Q learning all the way up to a deep Q network. And I'm going to try and do it with as little maths as possible. There's still some parts where I kind of had to put equation in there. I'm sorry, but it's just the only way to really express some of these ideas. And the other kind of thing I'm going to try and do is I'm not going to do like a medium post where I'm going to go through and go, okay, we write this line of code, and then this does this, and we write this line of code, and then this does this. I'm going to try and take us off in the paths where, like, if you were coding this from scratch yourself, you might think would be a good idea to go down, and you go down that path and you realize, oh, actually, this is a really terrible idea, and I can't get it to work, and you understand why we do things the way we do them. So, like, I guess what I'm trying to say is don't get too upset if a lot of these things like don't seem obvious by the end of this. This is like a complicated topic. It'd be very, very surprising to me if we were able to teach you guys a really detailed, nuanced understanding of reinforcement learning in 4 hours, right? It's just not going to happen. So these things are like going to take several layers of reinforcement, and this is just the first layer. The idea that you're going to get this broad, general understanding of how these things work. So let's like contextualize what I'm actually going to say. So this might be a bit small to read, so I'll read that for you. Basically, we've gone through at this point all of the tabular methods, right? So you guys should have an understanding of like how MDPs work, how we do things like TD, difference on that, and then how that leads to the tabular Q learning. So that's like all 100% central background to understanding the deep Q network, which is like the big paper that everyone talks about, right? So in between this paper, the network that learned how to play Atari and achieve super performance, there's kind of this intermediate step here, right? And this is this class of methods called neural Q learning. And all this refers to is the exact type of algorithm that Will talked about before, which is Q learning in the tabular case. But instead of a table, you use a neural network, right? And this class of methods is actually super old. It's like 15 years old. People thought of this almost as soon as they thought about how to do Q learning. And the problem with these is they're super brittle, they're super hard to train, and for a long time everyone thought like this would just never work. But what deep Q networks are a way of taking that core idea, applying a bunch of little tricks and techniques around it that make it stable. But before we can go to deep Q network, we have to go through this concept, which is neural Q learning. So why would we want to use a neural network in the first place, right? It's like a pretty good question. We've got a table, we know how to discretize actions. Okay, reinforcement learning and neural nets are kind of related, but why would we have any desire to try and merge these two things? The answer is, what happens when we're doing CartPole and we get into a state which we've never been in before, right? In the tabular case, what you have to do is you have to say, okay, I know nothing about this state, I'm going to filter back my value function through the Bellman equation and hope that I learn about it eventually. But if we approximate the Q function using a network, we can actually say, well, hang on, this state is really, really similar to another one I saw over here 20 time steps ago. Why don't I say that my Q value is pretty similar to that and then go with that and see how that works, right? So the key property of neural networks that we really want when we want to use in RL is it allows us to generalize into unseen states, right? So all of a sudden, you know what to do in a state you've never been in before, which is like this really powerful kind of scary property. And I've put this like picture of a chess board up here because I think like in CartPole it's pretty obvious, right? If the pole's a little bit to this side, you've been there before, the action's pretty similar to if it's, you know, like a degree less, right? But in almost every other game, you know, if you move a pawn one position in chess, it actually really fundamentally changes the strategy of the position, right? It's not just a single state. It's a really complex, you know, manifold of how all these things lie on some strategy surface. And so what a neural network is trying to do is learn this kind of complex linking between states in a way that we can't do with just like, you know, normal regression. So that's like generally one of the ideas that people say. They say, well, okay, I don't know how to generalize the unseen state, but why don't I just do like really basic, you know, linear interpolation across the states that I have seen. So if we imagine these red dots here are like all of our Q values that we have, and say we get a new one at 2.5, okay, I don't have a Q value here, but it's really easy for me to just take the average of the two around it, right? Why don't we just do that? And the answer to that is, yeah, you actually totally can. If you extend that into a way where everything becomes differential and the pre-processing tool is a convolutional layer, you actually come up with a really recent state-of-the-art algorithm, right, which is neural episodic control. So this idea works, but there's kind of really specific reasons why just a simple linear interpolation in the majority of environments is actually not the best solution. I'm going to basically keep using CartPole for all this stuff. So you guys, I assume, you've already been explaining all this stuff, like how the state space works, and you know, you've already coded up, so you know all that. The reason I'm going to keep using CartPole is because the training time is super quick. So we could do all this stuff I'm going to do with like an Atari game, but we all have to wait 2 hours for the thing to train before we can move forward, right? So CartPole you can solve with Tabular Approach. This is generally the point where you start to move towards more complex environments where you need these methods. But just for demonstration purposes, we're going to stick with CartPole. So using CartPole is like, it's kind of a good way to build up some intuition about what we're going to try and do here, right? So we have our like state space here, which is 4 variables. Just forget about that and imagine our state space as one continuous variable, right? So what I said before, where you know you have some sliding degree of the state and they're all defined in some measure of similarity to each other, right? So 2 really similar states are super close, 2 really different states are far apart. And then imagine the same thing for our action space, even though the CartPole is in it too. So for this you can just imagine maybe we actually have the degree of force, right? And then if it's positive it's to the left and it's negative it's to the right. Doesn't really matter, it's a good way to think about it. So we think about things like that, and we plot this on like a kind of a 2D grid, we end up with this thing called like a Q surface, right? And this is like very mathematically precise. So if anyone's done maths undergrad, don't get angry with me, please. But the idea is that we can have some state and action value like a Q function, and for every one of those pairs, there's a really specific defined utility or value of that function, right? And this is this Q surface, right? So it's probably not going to look like this in reality. It's not going to be smooth. It's probably going to be really like jointy and horrible. But the way I always think about these things is we have this surface which we're trying to optimize over, right? And so what our optimal policy is just moving to this top point, right? All we're trying to do is find like our maximum Q values. But in reinforcement learning, we don't have the Q values. So what we're actually doing is trying to learn this surface, right? So this, you can almost imagine as like the underlying dynamics of our environment, right? If the environment's fully known, and we know everything about it, we know where the best places to be, what the best actions are to take, and everything, right? In reinforcement learning, we imagine we don't know anything about the environment. We're just going to explore with it, try and figure it out. And through that process, we're going to try and get an idea of how this function looks, right? And so, as was probably explained, once you have these Q values, you can just straight away, extract the policy from that. If you have optimal Q values, you just take the best action at every point, and that's an optimum policy for it. So in the tabular case, what we're actually trying to do is we're trying to approximate this surface by sampling. So if anyone, I think someone that's done electrical engineering undergrad, right? There's some really strong analogies here to like sampling theory. So if I just go through here and I take a bunch of dots about the surface, I have a pretty good idea of its shape, right? But if that surface is really complicated and has lots of little turns and peaks and it's really like unsmooth, I need more and more and more dots, right? So that's our Q table getting bigger and bigger and bigger. And so what happens is when our environment becomes complex enough, it's just no longer feasible to actually sample the environment directly. It's just not possible, right? You need this, if you have some even second order like nonlinear dynamics, you need a state space table of like 10 to the 6 to get like rough coverage of it, right? So the memory requirements explode, all of a sudden, tabular case is useless. So the alternative to that, and what we do with neural nets, is we try to parameterize this function. So, you can imagine we have like a sine wave, right? And we can sample the sine wave, or we can just say y equals sine x, right? We have one parameter, and we know everything. And so the idea here is like, we use this kind of functional approximation, or parameterization, and we develop some equation which approximates this surface roughly, right? And if we have fewer parameters in that equation than we have rows in our table, we save memory, right? And we also allow us to generalize really naturally. Because we define, if I define an equation for the surface, I've defined it over the whole domain of that function, right? And it's smooth. So I can immediately pick out a point that I've never visited before and say, okay, this is the Q value for this point. So I just put that equation in there because that's like, that's Fourier approximation. Yeah, exactly. So there's really close analogs here between like, do you want to approximate a sine wave or signal by sampling, or do you want to just parameterize it and use it that way? So Fourier approximation is a really good approximation method, but one that's even better is neural networks. I just put in a little bit of point like CartPole is a really simple environment, but the underlying dynamics are semi-complicated. You can imagine how complicated it gets when we deal with things like tiring. And I wanted to put a caveat in here. So what I've just explained is like visualizing this Q surface in 3D, right? But really commonly what ends up happening is that our intuition in 3D, the way we think about these surfaces, does not extend at all to higher dimensions. So we're always dealing, when we're dealing with pretty much any RL problem, with a multiple, usually thousands of dimensions, right? You usually have thousands of state variables. That's the dimensionality of the problem. So when we have that, the Q surface exists in that dimensionality. And we just have to be really careful with applying our intuition and low 2 or 3D to these high dimension states. And I kind of want to put this example in here because I really like it. If you imagine we're just trying to find the volume of an N ball, so a ball that exists in N dimensions. A 2D N ball is just a circle. A 3D N ball is a sphere, right? So this is the area of 2D is the volume of the N ball, so it's pi r squared. And then the volume of the sphere is 4 pi r cubed. And if you just define this as, okay, the area inside a hole that is the same distance from the origin in every dimension, right? That's all we're defining this ball as. You can derive this general formula. But I wanted you guys to guess, or see if anyone knows, how does this volume increase as we go up through our dimensions? So this is the volume of a 1 unit 2D circle. It's the volume of the sphere. Does anyone want to guess where this graph goes or what happens to it? As we keep adding dimensions.
It's essentially discrete exponential, right? Because you're continually just adding in indices. So it's
yeah. So
it's
So you can probably go like something like this, right?
very sharp. No, much
Or
more.
explode, so
Yeah.
like that.
Yeah.
Okay. Anyone else want to guess?
I think
What was
it's
it there?
exponential. Maybe exponential. Maybe.
Exponential up, right? So the more dimensions we add, the more space there
Yeah,
is inside this thing.
start going up faster.
Right. Anyone have another theory or agree with that?
Would it be
So,
so?
let me just show you the answer. I think it's pretty more. So that's actually what happens.
Ooh.
Yeah. Right? So it turns out as we add dimensions to the sphere, the area inside it actually goes to 0. Just think about that for a minute. So why the hell does that happen, right? It just makes no sense at all when you think about it intuitively. You know, there's really no way to visualize 4 or 5D, so you can't picture in your head and try and figure out what's going on. But it turns out if you just define the maths and you say, okay, the whole is 1 unit and it's in every dimension from that thing, and I'll just work through the maths, that's what happens. And there is some intuition, like you might see pictures like this sometimes, and the idea is actually as you add dimensions, the amount of space starts to expand outwards, and the amount of space in the center just gets less and less and less. So you think of like an expansionary kind of thing, and you're left with less and less and less volume in the middle. And so you kind of see like the idea is that these points here kind of correspond to dimensions, and all the area starts to spread out to the end and corners of these dimensions.
So that's not the volume though. If you're setting the whole to 1, that means the relative volume, relative to the surface. The actual volume goes through that. No?
The actual volume
Okay.
goes to 0. Yeah.
Okay.
So this is the
Very,
actual
very-
volume defined by the equation there, which is R to the power of n.
Sorry?
Well, the actual equation for the volume there is R to the power of n, so that graph should have been
R is 1, so R to the power n was always 1.
resting constants. I maybe I can't see it.
That's
So
it, yeah.
Then it would just be constant if R is 1. The whole is the surface, and it's effectively the. I may have to take this on there. It's a
Yeah.
diversion.
Yeah, if anyone's unclear, like that's right. So that's part of the power of n, that's a gain function of that.
Correct.
So that's actually an increase in that. So that's the right way.
Correct.
And really interesting and weirdly, I find this really interesting, so I'm happy to talk about it. Like, there's nothing special about 5D, right? It just turns out 5D is what you get when you set the unit, the radius of the sphere 1. You set it to 2, it peaks out at like 10 or something. So it's really weird, strange result. But I just wanted to put that in there as a caveat. Like, I always try and visualize things in 2D, but often our intuition doesn't shift here. So it is a good case of like, sometimes you just have to find these things analytically and work with maths.
Is there a radius where the curve will change or for
At here,
no, so let's say for R value this is for 1, right?
Yeah.
So let's say we increase R to let's say 100 or 200, will the curve stay the same or
yeah, the shape of the curve stays the same, but it shifts. Yeah, it's pretty cool. Okay, yeah, so all of this boils down to like one thing, right? We're assuming that like our environment has some internal dynamics that we can better represent in a parameterized form or in an approximated form than just by sampling, right? So I put this quite easy. It's about the first thing that people realize when they learn about RL. Like, wow, this thing can make optimal actions for me. I'm going to apply to the stock market. I'm out of here. See ya, right? But it doesn't work like that because the dynamics of the stock market are, you could argue whether they're modelable or not. But for all intents and purposes, any function approximator is never going to be able to actually accurately represent that underlying dynamic. Right? It's just too complicated. If we're talking about, automatic trading. Yeah.
The fun really comes when everybody uses this model and you get like meta effects. Look up the
Bots trading bots.
look up the flash crash in I think 2012
Yeah.
or something. I can't remember. Where the whole market just like and then went back up.
So you can apply it to you can develop an RL bot for like, there's people that do it for position unloading, right? So if you accumulated a large amount of stock and you want to basically sell that in a way that won't move the market substantially, you want to do it in a way that is like going to get you the most value for your position, people have applied RL to that specific problem, and there's been some indication that might work, right? But if we're talking about the whole general stock market and modeling the whole thing, no neural net is ever going to be able to do that, at least for the foreseeable future. Yeah, so you sometimes see videos like this about how to predict stock prices. This does not work in this way. Yeah, so neural networks are universal approximators in theory. In practice, we're constrained by memory, computational power, and simulation accuracy such data we have access to. Cool. So this is kind of leads in nicely like over underfitting problem in RL. So you guys are probably all familiar with it in supervised learning, where like if we overtrain our neural net, we super specifically fit some function, and then the generalization property is terrible, right? Or maybe we only use like linear regression when the actual thing we're trying to fit is really complicated and we can't model it properly. So that would be like this example. And we actually run into this same problem in reinforcement learning. If the neural network we're using to approximate our Q surface, right? You can imagine that Q surface on the previous slide that kind of had bumps. If we were just using a linear, one-layer neural net, we'd never be able to approximate that, right? Because we can only generate a plane. Okay? But if we used a giant convnet or a resnet to approximate something that simple, it would just ultra fit to every little noisy bump in that data, and the generalization properties of it would be terrible, right? And would also be really hard to train. So one of the really important kind of intuition parts about when we use neural networks IRL is you have to understand how complicated is the underlying dynamics of this environment that I'm trying to model, and what's an appropriate complexity neural network to use that with. Okay? Because if you use one too simple, you're not going to capture it, it's not going to learn, you're never going to do anything. If you use one too hard, it'll overfit, and as we'll get to later, you'll find when you start to generate specific, ungeneralizable data, RL runs off the rails really quick. And it's also slower. So you want to use the simplest network that will learn the dynamics you want to model. And this is just a general context slide here, because I understand these words get thrown around and talked about a lot together. When we're talking about all these things, they're all in this umbrella term of AI, right? And when we're talking about reinforcement learning, I just want to make the point that reinforcement learning is actually really, really general. It's not a subfield of neural nets. It's not a subfield of deep learning. RL is about as general as it gets. If you can model something as an MVP, then RL is applicable. And then within reinforcement learning, we can use these function approximation methods, of which neural networks are a class, right? So there's no reason here you couldn't use a decision tree, right? People have done that and it kind of works. You can use an SVM, right? It would work. But at the moment we use neural networks. There's a couple of reasons for that. One is just the hype. Everyone does it, so everyone else does it, right? But then there's this appealing idea of we can use, the idea it's fully differentiable makes it really appealing, train the whole thing once. And it's also a nice idea that you really want this kind of gradient descent path, which has a lot of parallels to what we're trying to do in Q learning. But the key point, RL is this general overarching framework that neural networks slot into, not the other way around, right? People always get that sometimes mixed up. Okay, so that's my kind of background. Okay, so this is neural Q learning, right? So I just wanted to start with this to kind of show you where we're going to go. By the end of this little session, which should run for maybe about an hour and a half, we're going to implement this, right, as an extension from Q learning. And this is the general training flow. The idea is it's super, super similar, but we slot in a neural network instead of our Q table. It's literally the only difference. So that's just a broad picture. Don't have to understand everything like that. Oh yeah, but there is a kind of interesting thing that we can straight away see from this that maybe is worth talking about. we see we're doing like our exploration data collection one stage, and then we're going to train the network at the other stage, right? But these two neural networks are the same. So we're using a neural network to generate data, that is to generate our exploration policies and collect data from the environment. And we're going to use that data to construct the loss for the same neural network, which we're then going to train. So you can kind of start to see like these things, it's very like looping, it's very recurrent, it loops back on itself, right? And that's actually the main problem that we're going to go through and kind of drill down on and try and fix. So just before I jump into this stuff, is everyone familiar with neural nets? Everyone know what they are? Yeah, everyone's pretty cool. All right, I'll give like a really brief overview, right? Neural network is just several layers of nodes. They're all connected to each other at its most base form, right? And we have a really clever way of training the weights of these nodes so that this thing can approximate theoretically any function, right? That's the short version of what a neural network is. In neural Q learning, we just use dense nets or whatever, right? So all through this tutorial, we're just going to be using 2-layer, fully connected neural network because we don't need to model anything complicated. In DQ networks, which is like the specific algorithm which was used to win Atari, they use a thing called a convolutional neural net, which just means you take an image, you do a successive series of transforms, it automatically extracts like important features from that image, and then you feed that into fully connected layers and generate a policy. But this is also like one of the key differences, right? DQ networks refers to an algorithm, like a really specific type of algorithm in 2015 that was that Atari paper, probably everyone knows, right? Video breaker, being better than human. And so it's like all these specific things about how the component is set up and how it is trained and how it interacts with the learning method. But neural Q learning is just Q learning with neural networks. That's the difference here. So this is what we're talking about in this talk, just neural Q learning. Other people call it like if you Google neural Q learning, nothing will come up because the name I made up, right? Other people call it like neural dynamic programming, and I think approximate optimal control is another name. So it's like, it's a very ill-defined kind of little topic, but the way I understand it is actually like much clearer, I think, if you separate these two things. So you say neural Q learning is just Q learning with neural nets, and then deep QN is the specific algorithm. I think it makes things a bit clearer. So this is where we're at right now after Will's talk. We've got the Q learning kind of algorithm sorted. Okay? So here we're not doing any neural networks at all. We assume these are just tables or whatever. And the idea is we're going to go through, we explore our little environment, and after we explore, we calculate the target Q value, and then we do a kind of running update, right? So, we update our QSTAT by some learning rate that is the difference between our calculated state, which is calculated from the Bellman equation here, and our old state. Is everyone good with that, or should I run through that? Clear that, review Q learning? Because this is important to understand before we go on to it. So this is the key part, right? This equation. This is the Bellman equation, right? So the idea is we have some value function, we take a step, we get a new state, and we get a reward. That new state back into our Q function, and then we approximate the value of the previous state as being the reward plus a discounted value of that new state. Okay? So this is like this successive feedback mechanism through all of our states. This is normal Q learning. Go on, and you should know what's going on here. And then in neural Q learning, we just approximate this function with a neural net. That's all we're doing here. So everything is the same, just using neural net for the Q function. Yeah. So yeah, actually this is another view of the neural nets. So this is another important thing, right? I talked about Q function and how that works in RL, and there's a really analogous surface in neural nets, which is the loss surface. It's really important to not get these confused, and I got them confused for a long, long time. So when we talk about a neural network like this, right, we have some simple 4-layer neural net, right? We have state input, 4 hidden functions, and then we have action outputs, right? And then all of these links here have some weight attached to them. And what we're trying to do is set these weights so that the function that this neural network approximates is what we want, right? And to do that, we define a loss, which is basically like how far apart is the function we're generating from what we want. So that's all this means for you just go through, you say, okay, the value I wanted was yi, it's some distance apart from what is the correct answer, which is y hat, and then you go through, take that difference, square it, do that for all of the samples, and you've got some like pretty good approximation of how close and how far you were. And so a really common way that people think about this in neural networks is they think about it as a loss surface, okay? So they imagine, well, let's imagine this neural network, we fix everything except for 2 parameters, theta 0 and theta 1, right? So all these grayed out links, we just say there's some value, we set them, we're not going to touch them. And then what we can do is we can imagine, okay, well, depending on what values I set for these, it's going to directly affect my loss here, right? So if I have values here that make it really close to the function I want, my loss is going to get very, very small, right? If I have really terrible random values, my loss is high. And then you can plot this as like a 3D plot, and you can see, in this example, along the edges would be good values for theta, right? And then what we want to avoid would be this bulge in the middle, because it would correspond to a high loss. Okay? So you have this loss surface, and it's a really like natural intuitive way to think about how to tune parameters, but it's really distinct from the Q surface I talked about at the start. Okay, these are like completely different things. It's important to like kind of tease these apart. And we normally move across this surface by gradient descent, right? That's what gradient descent is. I'll talk about that a bit more later. But there's no reason you can't just randomly search for theta here. We don't have to do an informed search. It's just quick. Yeah, so the idea is we don't know what this surface looks like. We just set the weights, get a loss, and we have to kind of figure our way to the value. And so the way we kind of do that in neural networks is we use this method called gradient descent. And so gradient descent is basically, like I said, we don't know what the shape of the surface is like, so we just have a point, and then what we're trying to do is approximate the gradient at that point. So we just say, okay, I'm here, and the surface looks like this, so I'm just going to take a step of gamma magnitude in that direction. So the analogy here is like, you can imagine if you're standing on a mountain, and it's really, really foggy, you can't see anything, you can only look around you by 10 meters, and your job is to get to the bottom of the mountain. The easiest thing is to just start walking downhill where you're at, right? You don't have to plan some big, optimal path to the bottom of the mountain. Just walk downhill where you are, and then eventually you're probably going to get to the bottom of the mountain, right? It's a very, very similar thing here. We have our function, and we just take a step locally where it makes sense. We don't care about what the whole thing looks like. And so this equation, if you've been paying attention, probably looks like pretty similar, right? We've probably seen this before. So does anyone, because we haven't talked about gradient descent before, right? So where does that look? Does anyone know where that comes from, or what structure that looks a bit similar to? Maybe we'll talk about it. The weights? Yeah, it is actually very similar to weights. That's not what I was thinking of. I'll let you think about it. While we're thinking about it, this is what gradient descent looks like. It's a nice little visualization. So you imagine we have this surface. So in this context, this would be our loss surface. And we just take these little steps and we move across and eventually we converge to our optimal point, which would be a neural network that perfectly approximates our Q function. These are like different algorithms to do that. In our examples, we're going to use, not actually on here, but the stochastic gradient descent is like a classic algorithm that I talked about before. All these little variants of it. So there's lots of little ways you can like tweak these things, how it moves across the surface, but the idea is the same. If you're curious like about how this stuff works, look into a specific course for neural nets because it is actually really, really interesting. Yeah, so this looks familiar, right?
You mean a discount factor effectively?
Oh,
Like
close.
an exponentially weighted or
Very close. How many? How many? One more step. What's outside the Bellman equation? Q learning. Just looks like Q learning, right? So if we imagine this is a gradient of a function, right? When we do Q learning, we're trying to take the difference between a target and a current value, which is what the method of finite differences is to approximate gradient, right? You take a point, take another point, subtract it, and that's your gradient. And then gamma and alpha are both just step size functions. Q is the actual, value we're trying to update. So the whole thing is just gradient descent, right? Is Q learning just gradient descent? It's a really good question. I mean, it looks like it matches what? Turns out it's not. It's completely different. And this is like one of the really important things that separates reinforcement learning from supervised learning. Okay? So you might, I don't know if any of you guys have heard, so there's some of these people like Ian LeCun, they view the whole, you've got supervised learning, unsupervised learning, and RL. And he has this thing where he says, RL is the cherry on the cake. It's this tiny little thing that we will make deal with when everything else is organized. But it's pretty controversial. It's wrong. But reinforcement is actually much, much more difficult because when we're doing this gradient descent step, we don't actually have a ground truth, right? You think about this. The reason this equation isn't gradient descent is that the thing we're updating is in our target, right? So we don't have a y hat here, which is just some true, accurate value, okay? We're using our current best guess of our Q function to inform where we should move our Q function. So it looks back on itself like we saw in that first slide, and it really fundamentally changes the way we have to deal with all this stuff. Because all of a sudden, if this Q function starts to go off into a place that doesn't make sense, it just self-reinforces and self-reinforces, and it gets terrible. And you can't recover from it because you have no basic true value for Q you have access to. That's like another way of viewing the Q learning rule that makes it a bit clearer that it's not the same form as gradient descent. But the important thing to realize is, while this Q value here is being used to generate our loss, and we're using it, the thing that we're trying to train is being used to generate the loss of the thing we're trying to train, things become really, really complicated. And not complicated, but fundamentally different to supervised learning. Yes. Okay, so that was like a bit of, I apologize for the maths in that last slide, because I didn't know to do that. But this is the really simple thing. So in neural Q learning, we're trying to define a loss function that we can use to train a network, right? So we already know the Q learning update rule. The question in Q learning is like, okay, I've put a neural network into this equation. How do I train the neural network to actually learn what I want it to learn? And so when we want to train a neural network, we have to define a loss function, right? The loss function is what we saw in gradient descent that defined our parameter step size. So in neural Q learning, this is what we use, right? We use the square sum of the target value minus the current value. So all we have to do is we say, okay, this is it. We can calculate this by our exploration policy. We can get all these values empirically. We follow this formula, and then we just feed it into an automatic differentiation library, and it should converge the neural network to our Q function. We should have an optimal Q network, and then we've solved that problem, right? And this is way easier now because we have access to things like TensorFlow, where we just have to define the loss. In fact, before that, you would have to go through and build a gradient sampling, but we don't have to. So this is the key. This is kind of the key thing that makes neural Q learning work. We define this loss, we train the network, and we do everything else the same. And theoretically, this should work. Right? And from this point on, what I'm talking about is it's starting to become implementation choices as opposed to theory. So you can actually use different losses here, as long as the general structure is the same. We can use something like Google loss or something like that, and it'll all work. This is the simplest one. And that's what we're going to code up today. So, okay, we've got our loss function. That's easy. How are we going to structure the Q network so that any of this actually makes sense and we can actually get those values that we need? So, the intuitive way, the first way I would think to do it is we just, we're approximating the function, right? The function takes in states and it takes in actions and it gives us a value. So it would seem pretty easy. Okay, I set up my neural network that takes in the state vector, takes in the action vector, and then spits out a numerical value. Right? That seems like the easiest way to approximate that function. You can totally do it that way, but it's slow. For our implementation, this is what we're going to use. So, key thing, because we're doing this maximization step over A, to calculate this value means we have to calculate every single Q function here for st plus 1, right? So I can't possibly know what the max Q function is unless I know what they are for all A, right? It's just how max works. So because I have to calculate every single Q function here, we can actually kind of parallelize that in a neural net, and we can have, okay, we just put in our state, traverses through the neural network, and we get Q functions for every single action. Right? So that's a nice way to set that up. And it just means, okay, feed the state, I have all my Q actions, and I can do that max step really easy, and then I can just arg max these to find what the best action is. It's super simple. And for our implementation, we're going to use ReLUs, which is just activation function here and here. But an interesting question is normally you would do a soft max on this output, right? In a normal neural net. So do we need to do that in this Q network? Why or why not? Does anyone have any ideas? Kind of a giveaway that I'm asking a question. So we only care about the relative value of these Qs, right? We look at everything here is being, because the Q value is also the target as well as our predicted value, it's only recording what its relative value is. So we have no need to normalize these output nodes. We can just have them as raw values, and it's all good. So just to remember for the implementation, ReLU, nothing, right? That can just be raw. Cool, so now we're back at our kind of little structure, and it should make a bit more sense at this point. So when we're going to do our Q learning, we're going to do everything the same, except we kind of split things up into an exploration step and a training step. So for our exploration, we do everything the same. We start in some state ST. We feed that state into our neural network that we just showed before. So we just push the state vector in. Our neural network will take that and it will spit out our 3 Q values, or for the CartPole, 2 Q values, right? So we've got 2 Q values for that state, based on current belief in the network. And then we do our E3E step, which Paul talked about yesterday. So you have your Q values and then you just pick the biggest one, or with some small probability, you pick a random one. Right? And then we get our action. So at this point, we've fed in our state values and we've got an action back from our value network. all we have to do now is just feed that action to the environment. So we take the step, we go, okay, I'm in CartPole, the pole's here, I've fed that state into my network, and it's told me to take a step this way. So you just say, okay, take the step, right? The environment takes the action, it does something, and then the environment says, okay, now you're in this new state, st plus 1, and you also got some reward for that state or that action. Right? So at this point here, we've got our old state, the action we took, the reward we got for that action, and the state we ended up in. Right? So very simple, we just had our environment, took a step, and did that. Once we have all those 4 values, suddenly we have enough to train our network, right? So we do our exploration step, we get this length 4 tuple, and now we need to train. But before we just kind of do this equation, we need to know this value here, right? The max Q value of the state we ended up in, right? To figure this, we need to know Q st plus 1. So when we did it here, we fed in the state we were in. When we do it here, we're feeding in the next state. Okay? So these STs are different that are going into this network. This is where we were, this is where we ended up. So we feed this in, we get our Q values for the next state, and then we can calculate this max term. Okay? So we have a max term, we have our reward, we know the Q value, the previous state action pair, and that fully defines our loss. So then we have a loss, we say, okay, this is how far I think the network is from where it should be. You do a training step, network converges, you repeat over and over again. Right? So a couple of interesting questions here. Straight away is do we want to be doing one training step for every data collection step, right? Or maybe it's better to collect a bunch of data and then we do a training step overall. It's a good question, which we're going to get to later. So for online cube learning, we do 1, 1, 1, 1. We just iterate between these. Okay, so let's do some coding. This will hopefully become clearer. I'll put that link on the Slack maybe. And what we're going to do is I've kind of set up a skeleton for all this stuff. I've written all the messy, horrible TensorFlow code, and we're just going to try and implement some logic about how this stuff works. And I think maybe we'll do some live coding and we'll do it all together. Sure. And then I'll leave this slide up when we do. Yeah, so I'll just quickly go through the pseudocode as well. So we initialize our value function, which is just, we initialize some random Q network, right? I've written all that stuff, you don't have to do that. Then while our Q network is still training, as in while these weights are still moving around a fair bit, we haven't converged on some actual good Q network, we go through and we initialize an episode, right? We reset our environment, we get our first state, we take a step, put in some action, according to our iterating policy, we go to the then we execute the action, get the reward, and go to the next state. So these 2 lines here are our exploration policy in that top loop in here. And then we do our value function update with our SAI S-pair, which is our bottom step here in network training. And then the last thing we have to do is, okay, our current state becomes the next state we generate. And we move through. I'll leave this up here while we do this one. So if everyone goes to that URL and finds that repository, there's some code there that we'll start with. Okay, guys, let's do some code. So if you've got your laptop here, have a look at the NQL skeleton notebook. That's what I'm going to go through. So this has basically got a lot of the TensorFlow setup and structure that's not very related to RL, but it has none of the logic that we talked about, so we're going to implement that. Okay, so let's look at the start here. So can everyone read that, or do you want me to make it bigger at the back? Okay? Alright. So we've set up a bunch of hyperparameters which we'll use later. We've made the environment. And we've recorded our state dimension and our action space. Now, first thing we have to do, we need to define the placeholders of our network. So, based on the structure I talked about before, who wants to have an estimate of what state in should look like, knowing that we have this state dimension variable stored? So I'm pretty sure the argument here is, I should turn this off for a second. All right, well, let's do it first. Someone can get either some sunglasses or a pair of thongs if they get this right. How's that? So tf.placeholder, I'm pretty sure it's shape. I can't remember exactly. What should this be for our state in? Remember, we've got this variable right here as well. Okay, and also I'll clarify, in this situation, we're doing pure online learning, no batching. Okay. If you know, yell it out and you get something. Hey! That's it. Shape is stadium. John, on the signs. Thumbs? Large or what do we got?
We put some other sizes in there already.
There you go. Well done. Okay, so that's right. Let me be 100% sure that's right. Could be wrong. Okay, yeah, that's right. Okay, so none is state dim. Anyone, 3 guesses what this is going to be? Action dim. Okay, so that's fixed. What do we want our target in to be? So let's think about this, right? All of these are placeholders that we need to feed in to calculate our loss. What's target in gonna look like? Sorry?
Same shape as action.
So it should be action dim?
Yeah.
Anyone else got another guess? What is target in, first of all? What is this value?
It's a pure values for all action.
Let's look at this slide again, right? So what are we using for Q target? Q target is this value right here, right? So what kind of shape is this? First of all, okay, here's an easier question. What does our R plus gamma of the max look like? If we've defined, well, you know what this is, right? What the maximum Q value is going to be a real, right? A single scalar real. So a scalar real plus a reward is a scalar real. So if we want to subtract something from that, what would the target have to be? Scalar real. So the shape of this is 1. Okay, so we defined our placeholders, now we need to define our network. So let's look at our little network structure. So how do we, first of all, is everyone familiar with TensorFlow? I kind of assumed that, sorry. All right, well, if you're not, you're going to learn. Okay, so this is all TensorFlow. We're just going to make a call to a dense layer here. So this tf.layers.dense is basically defining one of these rows here, right? We feed in the previous layer, and it creates all these little weights for us, and it sets them up to be optimizable if we feed the final thing into an optimizer. So we don't have to worry about calculating the derivatives ourselves. So so what's happening here? Well, we've got one hidden layer that's taking our first state in, right? So that's defining this layer right here. The state in is our placeholder, which we've defined here. And we've just given it some hidden nodes hyperparameter, and we're using a ReLU activation. So all nothing new. And then we want to use a second hidden layer. So this, I don't even think, let's do it anyway. So second hidden layer can be exactly the same, right? So now we've created this, and now we want to create our final key value outputs. Now there's one little subtlety here, right? And that is, what activation function should we be using on the outputs? Right? I didn't talk about that. Why? Why would we use a softmax here? Remember, we have to use this in two situations, right? We have to use it one when we do our exploration, okay? And we have to use it one where we're going to calculate the max for our loss. And also remember, we want things to be as simple as possible, but not simpler.
Linear?
Sorry?
Linear?
Linear, as in just no activation. Bingo. So because everything here is relative, we actually don't need an activation on the output layer. When we do it here, we're just going to pick the biggest one anyway, if we do eGreedy. And when we do it here, it's a max. So actually activations on the output is unnecessary. So, and it actually, I don't know why this is, but when you implement it the way I've implemented it here, it makes it significantly better to not have a softmax activation. I haven't figured out why that is. But. Okay, so, but the shape needs to be, we need to specify the shape of the output here. So what's that? Has to be this, right? And then our activation, there's probably a nicer way to do this, but let's just do it like that. So we're making it nothing. And then I've already got this in here, which is for the Q action. What is this doing, right? This is actually doing our max term, but it's doing it in the computational graph for us. So this is reducing the, oh, interesting. All right, I got that wrong. So, no, I didn't, I'm right. This is basically taking our action in, which is the action we're going to select. This is here, right? And it's feeding that in. So this is going to get fed in as a one hot representation. So one hot just means we have the list of values, one of them is on, the rest is 0. So it's a mask, basically. People do image processing. And we're going to multiply that by Q values, which means we effectively select a single Q value. Then we reduce all that down in shape so that we get a scalar, right? That's all that line is doing. So it gives us the Q value of a specific action. That's what you can think about that state as doing. So we're done here, right? That's, I don't want to do that. Okay, so we've defined our placeholders, we've defined our network, now we just need to define the loss. So what did we say our loss was? Well, we've got it here, right? We want R plus gamma. I've already defined gamma up here, so we've got all our hyperparameters. This needs to be Q action minus what the hell did I put this? Okay, so what have I done here? Well, if you remember, I've actually, instead of having to calculate a target in, we do it outside of the computational graph. So this is another different thing in RL, supervised learning. We're actually going to step in and out of our computational graph. In TensorFlow, we build it up and then we make everything differentiable, and it's all encoded, right? But in RL, we're actually going to feed in a value, which we're going to calculate from the Bellman equation, which we use to define our loss, which we use to do the update. So actually, we're going to pass in this value here when we calculate it. We just pass it in as a placeholder. So that's why we do this target in minus Q action, which is the Q value of the selected action I talked about, which is this term here. And then we square it all, and that's our loss. So that's easy. And then we just feed that into our optimizer, and this optimizer, every time we call this TensorFlow op, it's going to take a step according to the way Atom Optimizer works to minimize this. So we collect, run this, collect, run this, collect, run this. I think you guys know eGreedy, so I'm not going to go through that. You probably already implemented that somewhere. This is just some TensorFlow boilerplate code, run everything. Now, this is where the kind of nuts and bolts for everything are happening, right? So what do? Okay, we want to take X number of episodes, right? Which means we want to run CartPole a certain number of times. That's just a hyperparameter we can set. As soon as we start a new episode, we reset the environment. This gives us our initial state, right? Which is stochastic and changes for CartPole. We then update our epsilon for eGreedy in the exact same way that you do in normal Q learning. And then we start to step through the episode. So at this point, we're starting to do these steps we've got in this graph, right? Okay, well, I can start to fill this in. So we want the next state, the reward, the done, and then this is, I'm pretty sure, some metadata that you can spit out from end. We just want to go m.step. What was that? Action. We just give it an action. Easy. And we've already calculated the action in this explore method, which I haven't implemented, but that's all we want to do. We want to say, okay, take one step according to the action we've picked based on our eGreedy exploration, right? And when we do that, our environment, our open our gym environment is going to give us the next state. It's going to give us the reward for taking that action, and it's going to tell us if we're finished or not, right? So what have we done here? We've effectively just passed through this gray box, right? So we've taken our action, moved through it, and then we've got all the information. Cool. So that first part is now done. Now, we need to calculate the Q values of this. So at some point up here, well, this is what the exploration thing does, right? It's just without the eGreedy at the moment. We feed in some state value into our network, and we get out the Q value estimates, right? We feed in the state, we get these values. So down here, we want to do the exact same thing. But because when we did it in explore here, we fed in the original state, we want to feed in next state. Oh. Okay, so does everyone understand what's going on? We've called our network once in this explore method, right? With our original state. We've got our initial Q values, which we've then used, or we should use, to do an eGreedy action selection. Okay, yeah.
I would just have a function just involve the inference, like, or why do we have a separate function for exploring one step?
Because in this one, you want to implement this eGreedy step here. Right, so I mean, let's do it because it's not clear. Where are we at? So this is what we would do here, right? We would say, okay, we get the Q estimates for the current state. So this is an inference step. And then we say, okay, let's generate a random number if the random number is less than E, we take a random action. If the random number is not less than E, we pick the Q estimate, which is with the largest value. Right? So it's just E greedy exploration. And then this is just converts it to one hot, like I talked about before. So it means that when we feed this action in, we can feed it in as a mask, right? So this line works, right? Okay, but here we don't need to do any exploration, right? When we're calling this inference step here, okay, we're done with our data collection now, and we just want to get the Q values of the next state so that we can accurately calculate our loss. Okay, so at this point we don't need to do it greedy. We just want to know what are these Q values, and so we just feed in the next state, and we get these next state Q values. And then we have a little kind of thing. If the episode is finished, you can't look one step ahead, right? The episode is done. So we just check, okay, if we're finished, then our loss is not this discounted reward, it's just the reward. I'm at the final state, so I can't do this. But if we're not, this is what we want to calculate, right? So our target value is gamma, well, it's reward plus gamma times the max of our next state Q values. Okay, so all that is these two terms here implemented in code. Right. Easy peasy. And now we've got everything, right? We've got everything we need to calculate the loss. We're going to feed this in. We've put this loss in our computational graph. So that was what this line does. So our Q action here is the multiplication of the, sorry, not that line, the loss. This line. We square the target in minus by the Q action. So we've calculated the target in, we're going to push it into the graph, minus it by the actual value and square it, and that's our loss. So that's everything done. This is what that looks like if you run it. So this is the simplest version of reinforcement learning with a neural network you can get. So it's very, very brutal. I've tuned these hyperparameters like a lot. You have to mess around with them a lot until it starts to do anything somewhat reasonable. And you see it's learning really slowly. So this has taken 400 episodes just to get a slight amount of learning going. And it's learning slowly and it's not good and it's very brittle, right? If you implement this yourself and you don't know what the hyperparameters are, you just think, wow, it's not learning at all, it's not working, right? There's a real sweet spot for the hyperparameters. So the emphasis here is this algorithm is super, super brittle, right? It's not something that I could take and apply on some other OpenAI gym environment and it would just work out of the box, right? I would have to tweak it, I have to run a hyperparameter search. But we can see that actually it's learning. So the neural network is learning a controller for the problem, which is nice. So we know it works. I think we're done. So it's actually somewhat stable learning. That's quite nice. Normally one of the things you see when you do neural Q learning is that learning rate is really unstable. So you'll see it go up and then it'll fail and then it'll come back and it'll be. This is, there you go, exactly like that. Maybe it's worth, There's reasons for that, but I'm not going to talk about it. I think I'm almost out of time. Okay, so where are we at? We're at something where the neural network is learning how to control a simple environment. It's very brittle, it's very unstable, and it's just not. This is fundamentally the same algorithm that DeepMind used on the Atari games, right? But looking at this, it looks nothing like it, right? This doesn't look even close to the level. So how do we go from this super simple example, which is pretty terrible, to a kind of system that can learn 30 different games stably without any hyperparameter tweaking, right? That's going from neural Q learning to deep Q networks.